Okay, so we have an example here that was on your last exam, the end of the chapter test on my math lab. And the problem states the speed of a moving walkway is about 4.5 feet per second. Walking on the moving walkway, it takes Maria a total of 20 seconds to travel 45 feet with the movement of the walkway and then back again against the movement of the walkway. What is Maria's normal walking speed? So we have a couple of things here. We have her going with the walkway, and we have her walking against the walkway. We have distance, we have the rate, and we have time. So the speed of the walkway is about 4.5 feet per second. And so if we're going with a walkway, we're getting our speed of our walk plus the 4.5 feet per second it's gonna increase how fast we're walking. And so maybe let's say that R is the rate of walking without the walkway. And so with the walkway, we would have this R plus 4.5. And walking on the moving walkway, it takes Maria a total of 20 seconds with it to travel 45 feet with the movement of the walkway and then back again against the movement of the walkway. So this is where there was some question, is this together? And we're thinking this is 45 feet there and then 45 feet back. It tells us that it takes a total of 20 seconds to travel 45 feet with the movement of the walkway and then back again. Oh, so that's a total of 20 seconds. Let me just pause. Okay, so we're thinking of that 45 feet there, 45 feet back right now. If we're going against the walkway, then it's the rate of your walk subtracting off 4.5 feet per second. So this would be R minus 4.5. We know that distance is equal to rate times time. Let's rewrite this as time. So time I know is equal to distance divided by rate. We know that the total time was 20 seconds. And so I'm thinking that our 20 seconds I know is equal to the distance over rate. So for the first one, which is 45 all over R plus 4.5. And then distance or time is equals to distance over rate. So for the time against, that is 45 all over R minus 4.5. So I have this 20 is equal to 45 over R plus 4.5 plus the time to come back, which was 45 all over R minus 4.5. And so we want to clear our fractions, and we can do that by multiplying both sides by our LCD. And our LCD in this case is R plus 4.5 all times R minus 4.5. So I get this 20 all times, because nothing's going to cancel when I multiply it on the left-hand side. And notice that this is a difference of squares. So I'm just going to FOIL that out on the left-hand side when I multiply it to 20. So A minus B times A plus B, that's A squared. So in our case, that's R squared minus B squared. And so 4.5 quantity squared gives us 20.25 is equal to, and so now when we distribute to the first fraction on the right-hand side of the equation, the r plus 4.5 is going to cancel, and you're going to be left with a 45 all times r minus 4.5. Plus, distributing the LCD to the second fraction on the right-hand side, the r minus 4.5 is going to cancel, and so we're going to get 45 all times r plus 4.5. So let's distribute and combine like terms. I'm going to move this up so we have some more room. And so distributing 20, we get 20r squared minus 20 times 20.5. That's going to give us 405 is equal to 45r minus, so 45 times 4.5. That gives us 202.5 plus 45r. 45 again times 4.5, so that could be plus 202.5. Okay, so we can combine like terms. On the right-hand side, nothing we can combine on the left-hand side. And so we have this 45r plus 45r is 90r. And we have this negative 202.5 plus 202.5, so those cancel. So looking at this, I noticed that I have a quadratic equation. So I want to set this equal to 0. So I want to get everything to one side of my equation. And so I can do that by subtracting 90r on both sides. Again, nothing is like terms, so I'm just going to rewrite it. Descending order of powers. So I have 20r squared minus 90r minus 405 is equal to 0. I don't see how to factor that. I do notice that at least they have a 5 in common that I can pull out of all those terms, but I'm not sure if that's even going to help me very much to see what to factor, but I can try. And so if I factor out a 5 from all 3 of those terms, I get 5 all times the quantity 4r squared minus, well, 5 goes into 90. Let me just think about this for a second. 18 times. So 18r minus 5 goes into 405. That is 81 times. This looks like might be a difference of squares. So I think that this might factor, and I can either use the quadratic formula, I can use my AC method, I can do trial and error, and I'm just going to do trial and error real quick. I think that's the same thing as 2r. Maybe. Nope, it's not. Okay, I'm going to use the quadratic formula. And so I have negative b. So that's going to be positive 18 plus or minus the square root of 18 squared, or negative 18 squared, which is the same thing as 18 squared, which is 324, minus 4 times a, which is 4, which is 16, times c, which is negative 81. And so we have a minus, that's going to be a plus there, minus and a minus. So this is 1,296 all over 2 times a, so 2 times 4, which is 8. So 324 plus 1,296. That gives us 1,620 all over 8. So taking the square root of that 1,620, oops, it doesn't go unevenly. Okay. All over 8. I'm thinking I can pull stuff out if I wanted to. I see that 1,620 at least has 4 that goes in there, which is a perfect square. I'm not sure how much. I mean, you guys, I took back and I said you could use a calculator. So let's just use a calculator. So let's do 18 plus the square root of 1,620 divide by 8. And so this right here is approximately 7.28. If I subtracted 18 minus the square root of 1,620 and I divided by 8, this gives me negative 2.78, rounding to the nearest hundreds. But we're talking about distance or rate. And so it doesn't make sense to be traveling a negative speed. And so what is her normal walking speed? Well, this is in terms of feet per second. So 7.28 feet per second. Okay. So we're looking at functions, and we've been talking about finding the domain of functions, looking and telling if an equation is a function or not. But now this example says, let's find the domain of p of x equals the square root of 2 all over x minus 1. So when we're looking for the domain, we're looking for trouble spots. And trouble spots occur, values which set our denominator equal to 0, or values which give us a negative number underneath an even powered radical. So I notice I have a square root, so I might have some problems here. I also notice that I have 2 over x minus 1. I have a variable in the denominator, so I'm going to have a problem there. I notice that I need what's underneath the radical, 2 over x minus 1. This has to be greater than 0 in order to spit back a real number when I put in a value for x. I notice that x minus 1 cannot be 0. So I notice that x has to be, or x cannot be 0. Add 1 to both sides. X cannot be 1. This is where we're going to have some problems. This is a rational inequality. 2 over x minus 1 is greater than 0. We actually haven't talked about rational inequalities except for that one that I had to go over again. But that we haven't covered that in our textbook. We have to be careful of a couple things. So I need to look at my denominator, x minus 1. I notice that that has to spit out something that is positive. I have 2 in the numerator, so I know 2 is always going to be positive. If I had x minus 1 was a value which was less than 0, then I'd have 2 over a negative number, which is negative, and that is not greater than 0. So kind of some reasoning in here, I can tell to myself that I know that x minus 1, in order for it to be a positive, or 2 over x minus 1 to be a positive number, x minus 1 has to be positive. And so if I solve this linear inequality, I would just add 1 to both sides. So x has to be greater than 1. Any number that would be less than 1 would give us a negative number underneath the radical, and then that wouldn't be part of our domain. That would spit out a imaginary number. And so for our domain in this piece, x has to be greater than 1. So properties of functions. So this is just notation. If you were adding 2 functions together, let's say we had some function f of x and we wanted to add it to some function g of x, Another way that we could write this is parentheses f plus g parentheses x. Do not think of this as you're factoring out at x from each one of those f of x and g of x, because that's not what that means. That means that this is a function in terms of our independent variable x for f, and a function g of x with an independent variable x. Later on, when you get into maybe calculus, they'll just write the function f plus g. You don't even have to have the x in there. It's just represented that that is talking about a function of, and not just one variable. Same thing if there was subtraction. So if we wanted to take some f of x minus g of x, this can be written as f minus g in parentheses x, or f minus g. If we were multiplying two functions together, f of x times g of x. Another way to write this is f times g inside parentheses, and then outside a parentheses x. And then the last one, if we had f of x divided by g of x, another way to write this is parentheses f over g, and your parentheses x, or f over g. So since we have a denominator here and we have a variable in our denominator, we have to say that g of x cannot equal 0. Okay. So if we were looking at the domain of these properties, well, we would have to look at the domain of each piece. So I would have to look at the domain of f of x, and I'd have to look at the domain of g of x. And then we would take what they share in common. So the domain of these properties is equal to another way to say this is the intersection. What they have in common is equal to the intersection of the sets of the domains. Only thing that we have to be careful is with that last property is that g of x also cannot equal 0. So let's look at something. Let's pull out an example. So let's say that we are given that f of x is equal to the absolute value of x, and g of x is equal to just x. So for the given function f and g, find the following parts. So let's say for part A, this would say f plus g of x. So that's just saying I'm taking my function f of x and adding it to my function of g of x. Well, my function of f of x is just the absolute value of x plus my function of g of x, which is x. And I can't simplify this because of the absolute value in here. And so I would just leave it like this. If it asked us to find, how about f minus g of -4? So there's a couple ways that we can do this. We can look at this as looking at f of -4 minus g of -4. So this is representing, this -4 inside the parentheses is representing that we're going to plug in -4 wherever we see an x in our functions of f of x and g of x, or plug in -4 wherever we see an x. So f of -4, we have the absolute value of -4 minus g of -4. So plugging in -4 wherever I see an x. So this would be minus -4. So we can simplify this. Absolute value of -4 is 4. Minus a negative is plus. So I have 4 plus 4, which is 8. We could have done the process a little differently. We could have, if we were trying to find f minus g of -4, we could first find f minus g of x. And if we did that, f of x again was the absolute value of x minus g of x, which was just x. And then find f minus g of -4. So now we have what f minus g of x is. We can now go in and plug in -4 wherever we see an x and the difference of the two functions. And we can see that we're going to get the absolute value of -4, which is 4, minus a -4, which is plus 4, which again gives us 8. So either way, you're going to get the same result. Let's try another one. Let's say that we're given f of x is the square root of x minus 1, and g of x is equal to the square root of 4 minus x. What if it said find the domain? Of, let's just start with f of x. Let's just change it. How about f times g of x? To find the domain, we have to look at the domain of each piece. So we want to find the domain of f of x. But we have a radical, and so we have to be careful. And it's an even powered radical. So everything underneath the radical has to be greater than, in this case, can also equal 0. So x minus 1 has to be greater than or equal to 0, because we can take the square root of 0 and get back 0. And so if we add 1 to both sides, we get x has to be greater than or equal to 1. We want to find the domain of our other function, g of x. And so again, we have a radical, so we need to take what's underneath the radical and we need to set that greater than or equal to 0 because it's not in the denominator. So 4 minus x greater than or equal to 0. I'm going to add x to both sides, so I have 4 is greater than or equal to x, but I like my x value on the left-hand side just so it makes more sense to me. So I can rewrite this as the same thing as x is less than or equal to 4. We want to take what they share in common. So if we graph the one set above the x-axis or this axis and the other set below, we're going to look at where the shaded region is in common. And so let's see. So we have this one that x is greater than or equal to 1. And that would be everything that is equal to 1 and to the right. And then we have everything less than or equal to 4. So we have x equals 4 and everything to the left. So what they share in common what the two sets share in common is the domain of that operation. So in this case, it's going to be everything from 1 to 4. Another way to state that is inequality notation, but interval notation, we'd have a bracket on the 1, 4 bracket. Okay, so that is our domain. Of f times g. If it had asked us with the division, maybe f divided by g, we'd have to put on a little more of a stipulation there. So say it said find the domain of f divided by g of x. Only other thing that we have to add in there is that g of x cannot be 0. So we want to find when is g of x equal to 0. So we know that square root of 4 minus x cannot equal 0. And so if we go through and we solve for that, we can find out what values of x that equal to 0. And you can probably just look at it and see. But if you couldn't, we could use that property where we can square both sides to clear that radical. And we get 4 minus x cannot equal 0. Add x on both sides. So we say x cannot be 4. So only difference here is that we're not including 4. So the domain of f divided by g that is going to give me 1, I'm going to include it, 4, I'm not going to include it. Or 1 is less than or equal to x is strictly less than 4. Let's do part B or C. Let's look at what would have f times g be though. Well, that would have been our function f of x, which is the square root of x minus 1. All times our function g of x, which is the square root of 4 minus x. Well, they're both radicals. We've made sure that nothing's going to give us a negative number underneath the radicals. And so this is equal to the square root of x minus 1, what was underneath the one radical, all times 4 minus x, what was underneath the other radical. If I distribute this out, and I can simplify a little bit, it's not going to really help me do anything but to simplify it down, but we can if we want. I would probably leave it like that. So orders, so just the notation, operations of functions, being able to find the domain after we take the operation of the two functions. Let's see if you guys have any questions on that. So given f of x equals 1 over x and f divided by g of x is x plus 1 all over x squared minus x, we want to find g. Okay, so let's write this out, okay? We're given that, I wanted to write, we want to find g, but we're given that f divided by g, which is x plus 1 all over x squared minus x. This is equal to our f function. And our f function that we know is 1 over x. Divided by our g function. And that's what we're trying to find. So we're trying to find g. We have a fraction equal fraction. So we could do cross multiplication if we'd like. So if I do that, I get 1x all times x squared minus x is equal to my function g all times x plus 1. Notice if I distribute my 1 over x to x squared plus or minus x, our x's are going to go away. So x squared over x, that's just a single x. Minus x times 1 over x, x's cancel, and that just gives me a 1. Equals g all times x plus 1. So I can see that I'm going to get g by itself by dividing both sides by x plus 1. So it looks like g is equal to x minus 1 all over x plus 1. And I just want us to show this. Let's go back and show that if we divide f of x divided by g of x, we do get, and simplify, we get x plus 1 over x squared minus x, just to kind of review how to deal with complex fractions. So let's show it. So let's look at f of x over g of x. So our f of x function we were given was 1 over x all over our g of x function, which we just found to be this x minus 1 all over x plus 1. Couple ways that we can deal with this. I have a single fraction over a single fraction. So we can think of it as the fraction in our numerator, 1 over x. You can write it this way, as divided by fraction in the denominator, x minus 1 all over x plus 1. But division with fractions, we look at the first fraction, which is 1 over x, times the reciprocal of the second fraction. So flipping it, we get x plus 1 all over x minus 1. which I see if I distribute my 1 in the numerator, I get x plus 1 all over. And if I distribute my x in the denominator, I get x squared minus x. And we were just showing what we did was correct. And we would get back x plus 1 over x squared minus x, which we did. So we found the correct g of x. So we're looking at f of x now is equal to 1 over x plus 3. The question asks us to find the difference quotient of f of x. And the different quotients, if you forgot, was this rational expression f of x plus h minus f of x all over h. And so if you want to break this down into pieces, that helps you at first. Let's look at first, what is f of x plus h? All that's telling me to do is go back into my function, f of x, and wherever I see an x, I'm going to replace it with x plus h. So I have, this is equal to 1. I see an x there. So a lot of times I'll just put parentheses of where I'm going to go back in and substitute in. So parentheses plus 3. So now we're going to go in and replace where that parentheses is, where the x was in our original function, with x plus h. And so this would give us 1 over, I don't need those parentheses there, x plus h plus 3 in the denominator. So putting it together, f of x plus h, I'm going to then subtract off f of x, and then I'm going to put it all over the variable h. Well, f of x plus h we just found was 1 all over x plus h plus 3 minus f of x. So subtracting this off. So I have minus 1 over x plus 3. And then we're putting this all over the variable of h. So we have a complex fraction, fractions within fractions. I cannot deal with this the same way I dealt with that other one because it's not a single fraction over a single fraction. So I tend to like the other method of solving these is where you look at the fractions within the main fraction. So I have 2 fractions within this one fraction, and I find the LCD. And so the LCD is going to be what's in the denominator of the first fraction in that numerator, x plus h plus 3, times the other denominator, x plus 3. So we're going to multiply this by a fancy one. And that fancy one is going to be that LCD over the LCD. It helps you write that LCD over 1, at least for the numerator in this case. So we got to distribute this to each piece in the numerator. And when we do that, the fraction is going to go away. So when we distribute it to the first piece, that x plus h plus 3 goes away, just leaving you with x plus 3 minus, when we distribute it to the second fraction, the x plus 3's go away. We need parentheses around this. And we're left with x plus h plus 3. And then we're going to put that all over this h times, we got to distribute, but I'm not going to distribute it out. I'm just going to leave it as x plus h plus 3. That in parentheses, all times parentheses x plus 3. So we're almost there. We're going to distribute this negative and then combine like terms in the numerator. So we have x plus 3. Distributing the negative, we get negative or minus x minus h minus 3 all over h all times x plus h plus 3. That quantity times the quantity x plus 3 in the denominator. So notice you have an x minus x in the numerator, those cancel out, and we have a 3 minus 3 in the numerator, and that also cancels out. So all we're left with in that numerator is a negative h. But I notice that I have an h that's a factor down here in the denominator. So that's actually can cancel out. So I have a negative h all over h times the quantity x plus h plus 3 times the quantity x plus 3. Leaving us with negative 1 in our numerator all over parentheses x plus h plus 3 all times x plus 3. And so that's the difference quotient of our original function, 1 over x plus 3. So the next section goes over graphs of functions. So recall what it means to be a function. For every value of x that is in the domain, it corresponds to exactly one y value in the range. And so if you're given a graph, you can test to see if that is a graph of a function by what is called the vertical line test. So if we can draw a vertical line anywhere on our graph and it only intersects the graph at most once, then it is going to be a function. And so if I draw a vertical line here, I notice that it's only crossing once. If I draw it anywhere on this, I can see that there's no place where it's going to cross more than once. I notice over here, it's actually not crossing anything, but that's because it's not, that picture is not there. It's not in the domain. And so by the vertical line test, if you can draw a vertical line anywhere on the graph, and it intersects at most one time, then the graph is a function. So looking at this, I can say that this picture that I had given you guys was a function. If we look at this, given a graph, you should be able to figure out what the domain and the range is. And so recall domain, that's all the x values that we're using. And so on the graph, all the x values that we're using, well, because this is a point here, the most left bound, that is telling me that this is not continuing on forever. If this had been an arrow in here, that would have continued to go upwards and would have never stopped. It would continue in that direction forever. But because there's a point there, that tells me that that stops. And so the smallest x value that I'm hitting is -4. It's included because this is a solid point, so less than or equal to x. And it's hitting all the x values from -4 until we get to the x value of 6. Another way to write this in interval notation, it would have been bracket -4, 6 bracket. The range are all the y values that we're hitting. So I always go smallest to largest. And so if we look at this graph, the smallest y value that we're hitting here is at -2. So -2 is less than or equal to y, is less than or equal to, and the highest y value looks like this graph is hitting when y is 3. So interval notation, in this case, the only time that we use y values using interval notation is when we're talking about range. And so we have a bracket -2, comma, 3 bracket. Looking at this, you should be able to answer certain questions. So for instance, if they said find f of -2, you need to notice or know what that is saying and what it's representing. Basically, this is saying is we're finding y when x equals 2, x equals -2. Right, so when x is -2, I can see that my y value here is 1. So f of -2, we can say is equal to 1. You should be able to find intercepts by looking at a graph. So if it says, what is the X-intercepts? Let's find the X-intercepts. So these are spots where the graph is touching or crossing the x-axis. And so if we look at where it's touching or crossing the x-axis, you can see that that's going in multiple spots. We have a point here at 0, 0, a point at 4, 0, and a point at 6, 0. So in this case, we have 3 x-intercepts at 0, 0, 4, 0, and 6, 0. And then the y-intercepts well, if we look at this, the y-intercept is where it's crossing the y-axis, and then in this case, there's only one spot, or touching the y-axis. There's only one spot, which is at 0, 0. You should be able to find all x values that give you a certain y value. And so how that would be written is, if it said find x such that, let's say f of x is equal to 1. So this is asking us to find all the x values that give us a y value 1. So let's find 1, y equals 1 on the graph. Let's draw a horizontal line through here. And so notice that I can see that this graph is going to hit y equals 1 in multiple spots. When x is -2, we're going to estimate this. We're going to say about 4.1. Let's just estimate this. So let's say that this is about 5.9. So there's 3 different x values that give us a y value 1. So at x equals -2, x is approximately 4.1, and x is approximately, I'm just going to do approximately 5.9. That funky equal sign. wavy equal sign means that I approximated around it. I'm going to cover it. I know this is in the next section, but it's pretty much following the same thing. So I'm going to just cover it right now. You should be able to look at where a graph is increasing and decreasing and where it's constant. So we can say that a graph is increasing. If you look at the graph, you're reading the graph like we read books in at least the US, left to right. So as you're reading left to right, is the graph going up or is it going down? Think about if you were walking on it, we're moving left to right. If you were walking on this, would you be going uphill or would you be going downhill? And so if we're going downhill, we're decreasing. If we're walking uphill, we're increasing. And so if it asked me to find where is this decreasing, let's find the intervals. Where the graph is increasing and decreasing. And let's put it in interval notation. Okay, so let's look at decreasing first. Doesn't matter. So if I'm looking at the graph and I'm looking at where is this decreasing? So where is this going down from left to right? Well, I notice that I'm starting here at -4. And if I can continue, I can continue until I hit this value x equals 2. Then I'm going to start to go back uphill. But then I notice again, when x is 5, that I start to go downhill until I hit x equals 6. So I'm decreasing. Because this is an endpoint and it's not going on forever, I'm going to put a bracket here at -4. I'm starting at -4, comma, I'm stopping when x is 2. And that's where I'm going to change direction. So I'm just going to put a parentheses here. So I'm decreasing from x equals -4 to 2, union. So I'm starting, but this is also where it's stopping to be a max or increasing. So I'm going to put parentheses. I'm starting to decrease from 5, comma, and I'm going to stop at 6. And because this is an endpoint, I'm going to put a bracket. So these are all x values where I'm going down. If I look at all the y values, I'm sorry, x values of where I'm increasing. So this is where I'm going up from left to right. And if I'm going up from left to right, I can see I'm going up just in this little piece on my graph. But to write this in interval notation, I'm looking at all the x values, not looking at any of the y's. And so it's starting when x is 2, parentheses 2, and it's stopping at the x value of 5. So notice if you didn't know that we're talking about interval notation and you saw parentheses 2, comma 5 parentheses, you might think that that's a point, but that's not. Those are all the x values in between 2 and 5. Okay, so we're going to have a little bit of fun and do a little bit of review of what we've been covering with functions. And so it's going to be the class against me. You guys can be team number 1, even though I'm only 1. And you guys can choose what you want. I'll give you first dibs to steal. or to get it correct, and they'll see who can win. And so I'm going to ask the class what they want. I'll pull that up and I'll read it, and then I'll pause the video. So let me pause it while I get what you guys want to do. Okay, so you guys chose domain and range for 300. Let's see what we got here. So find the domain and the range of the following function. So looking at the following, could you tell what the domain and the range is? So I'm going to pause it and then we'll discuss it. So I made it so you can see the whole picture. So just there that is. Okay, so you guys got it right. You said that the domain was between negative 1.25 and 3.25, and those are your X values. And so if you look at the X value here, and we can estimate, so about negative 1.25, and I would have given you that. And this is about 3.25. And so all the X values that we're hitting are between negative 1.25 and 3.25. The range are all the Y values you're hitting. And so the smallest Y value that we're hitting here is that -4. And the largest Y value that we're hitting is 0. And so we're hitting all the Y values between -4 and 0. And so you guys got that. So I need to give you points. And so team 1, you got 300 points. Just gave you 300 points. You didn't see that. We'll do space bar just show that you're right. Oh. Okay. We got the domain and the range. And this is telling me it's not a function. And can someone tell me why this is not a function?
I'm pretty sure it's because it doesn't pass the line test, right?
Right.
So yeah, since it's a circle and it's not a line, it doesn't pass the vertical line test because it passes through 2 Y coordinates, I believe. And yeah, I don't know if I'm pretty sure 2 X coordinates too.
Right. It's only 1 X coordinate, but for 1 X value, there's multiple places for 1 X value that we're getting multiple Y values. And so like for this example, when X is 2, right, it's crossing here for Y is, negative, I don't know, 0.25 and negative 3.75. And so there's multiple places we can draw infinite number of places between that negative 1.25 and 3.25 where we're going to cross more than once. And so by that, for 1 input, we're getting back multiple outputs. So that tells me it's not a function. Okay. I could still ask you what the domain and the range is of a graph that's not a function. So that I think maybe was a trick question when it was talking to us. So let's go to the next one. Okay, so we got taken away from us 300 from domain range. Everything else is open on the board. What would you guys like to look at?
Draw the function 100.
Okay, so draw the function 100. So draw a function that is never decreasing with a range of -5, so including -5 to 6, but not including. Okay, so this has gotten some good discussion in and trying to look at this. So one of the things was like, what about a U? But then looking at it, notice that a U wouldn't work because this is decreasing here. And then talking about, maybe a vertical line between -5 and 6, like this, where open circle and a solid circle. The problem is that doesn't represent a function because vertical lines for 1 X value has an infinite number of Y values in between. And for our 1 X value, we can only get back exactly, or at least 1 Y value, only 1 Y value. if it's in the domain. So what I had here and pictured is something that could work. This is increasing, never decreasing. It didn't matter. It didn't tell me what my domain was, so I could start anywhere, right? So this could have been a -3. And this could have stopped at x = 2. And this would hit all my y values between -5 and up to 6, but not including 6. So this is one example that would work for what we were talking about. Okay, so you guys, this is as far as we got in the last bit of class. So you guys were the winners. I will give you guys credit for being around and playing Jeopardy today. So don't worry about when you see that in-class exercise come up on Canvas. You've been in class, you were here, you participated. I'll just go ahead and give you points. I am going to include an assignment for those people that miss class that they can turn in and get the participation points. So, but you don't have to worry about that. And you might have seen that I did that for you guys on Tuesday because you did an in-class exercise on Tuesday. So if you weren't in class on Tuesday, you can go pull that up from Canvas, do it, and turn it in.